Hello, good afternoon, everyone. Thank you for taking the time to make it out to today's session. My name is Daryl Saraspe. I'm a geotechnical engineer here at Midas, and I'll be giving today's presentation on soil structure interaction for short excavations using 3D finite element modeling analysis. And also, this is a great opportunity for those of you who are looking to GTS&X to see how this program is used specifically for these types of applications. So before I get into the presentation itself, I just want to go over a few things. So for those of you who are new to GoToWebinar, please just, if you can hear me, just use the input window on the GoToMeeting icon just to raise your hand. And if anybody's having trouble hearing me, feel free to just type into the chat box, and I'll do my best to adjust the audio for you. So also make sure that every once in a while you wiggle your mouse across your screen, otherwise a screensaver will go on. And also make sure to maximize your screen so you can get the full view of what I'm showing you here. And another sort of icons, or for those of you who aren't familiar with the icons of GoToMeeting, you can just use this icon here, the red arrow, to hide the dialog box. And once again, if anybody has any questions at all, feel free to type into the chat box and press send. So as far as sort of questions relating to the webinar itself, for any sort of technical questions, just please save those for later, and we can get back to you later on, just because we're on a bit of a time constraint here. So once again, though, if you do have any issues with the audio, or if you can't hear me, any technical issues, feel free to just let me know through the chat box, and I'll be checking it periodically. Okay, so as far as the overview of the presentation, this is what we'll be doing today. We'll just give a brief introduction to Midas, our company, our services, what we can do for you. Next, we'll go into principles of short excavations, as well as numerical analysis in short excavations. So this is just sort of a technical background to short excavation design and analysis, and then also how it pertains to numerical analysis today. And then last, for these two sessions here, I'll give an introduction to GTS&X, what the program is, what it can do for you, and then I'll give a brief demonstration on how the program can be used for a short excavation type project. Okay, so Midas, we are currently the world's leading engineering software provider. Currently, we have 6 main branch offices across the world. So currently, I'm broadcasting from our American headquarters here in New York City, but we also do have offices in Japan, in South Korea, China, India, England, and Russia. And in addition to those branch offices, we also have various distributors around the world. So, our software is used very extensively by many leading engineering firms. And we hope to continue to provide our services to many engineers for their projects. So we hope that through this presentation you can gain some trust and some interest in our programs and our services, and that we can provide you those same services that have helped so many engineers so far. Okay, so now we have a couple of sort of high-end projects that we like to sort of share. So first, there's the Mohr Coulomb Tower in the United Arab Emirates. This was modeled and analyzed with our engineering program. So the foundation was modeled with actually GTS, and then the superstructure was modeled with Midas Gen. And then the Beijing National Stadium in China was modeled and analyzed with our programs, as well as the Sutong Bridge in China. This was modeled with Midas Civil, which is our finite element analysis bridge program. And also the Rusky Island Bridge in Russia was modeled with Midas Civil. Then the Shanghai Expo Pavilion in China, and of course the Incheon Bridge in Korea. So these are just a couple of examples of sort of larger high-end projects that our programs have been used for, but also keep in mind that our programs are used for sort of typical everyday projects as well, so it's very versatile in that respect. Okay, so in addition to our software, another great and valuable service that we provide is online training. So, as you can see to these pictures on the right here, we have various sort of live seminars and conferences throughout the year. These are just a couple of pictures from our bridge seminar in New York City that took place recently. And then here's some other pictures from sort of seminars we've had around the world. So in Asia as well as Europe especially, we're having a lot of conferences. So just keep a lookout for the invitations that we send you. These are great opportunities to learn about new technology, to network, and then also to sort of gain some understanding of modern design practices that are being used. So these services, or these seminars themselves, they're free, and so they're no cost. And then also, in addition to these live seminars, we have many sort of online sessions, such as the one you're attending today, where you can continue to expand your professional knowledge, and where you can continue to see what options you have out there that are available to you to help you work with greater efficiency. This particular session isn't interactive, but if you do have interest in learning more about our programs, or if you want to, I guess maybe set up an individual session, you could follow up with your local representative, and we could set up an individual interactive session where you can answer your questions directly, and maybe go over a specific project type that you have in mind. So these are interactive and they're customized sessions. Okay, and then as far as the relationship that we have with our clients, we like to make sure that they're ongoing. So usually the relationship follows this sort of process, or this sort of diagram here. So first and foremost, we introduce ourselves, we introduce our programs and our services, which is for those of you who are still sort of new to Midas or what we do, this is sort of the stage where you're at now. And then hopefully what we can do is you can have your interest piqued, and that you can develop, I guess, a desire to look more into the programs and to evaluate it for yourself. So what you can do actually with all of our programs is you can download a free 30-day trial version that you can use to evaluate, to make sure that this is something that could really be of use to you. And during this evaluation process, we can provide the customized training and one-on-one sessions to help answer any of your questions. And then from that point on, if you decide to purchase the program, the relationship doesn't end there. From that point on, we help you develop your skills through training and tech support. So after for example, a client purchases a new license, or we have a new client anyway, what we do is we make sure to set up a training schedule to help them learn how to use the software, and then also technical support. So when they're using it for an actual project, they can have all the guidance they need to take full advantage of all the program's capabilities. And then through these two steps here, training and tech support, we help our clients become expert level users. So then, they have this very powerful tool, and then also the skill set to utilize that tool to its maximum capabilities. And then from that point on, even after our clients reach this sort of expert level skill set, there's still always room for improvement. That's why we continue to have technical seminars. So it's really through this partnership that we help all of our clients learn and grow as professionals, and really enhance their skill set to become better at their job, and also more marketable in the workforce. And then as far as the technical support is concerned, so this this relationship, or this flowchart, sort of demonstrates what we do for our clients. So we're with you from the very beginning to the very end of the modeling process. So usually what will happen is, as our client will send in maybe a picture of an AutoCAD drawing that they want to model on our program, and we'll help them step by step to create that model. And then ultimately to create the elements, the constitutive models, to define those, and then to create the mesh set, the completed model, and then to the result extraction. So just keep in mind that if you decide to go with our software, you'll also be getting our services, our support, so that you won't be left alone with the program. You'll have our full support to help make sure that the project or the model that you have created meets those high standards of quality that you have set for yourself. Okay, so now let's go into some principles of short excavations. So what I'll be doing in this sort of section is I'll be going over the conventional methods of short excavation design or analysis. Okay, so first let's go over just some basic principles of deep excavations. So a deep excavation involves the removal of soil to construct a foundation or underground structure. So as geotechnical engineers, I'm sure you're all very familiar with this process. Whenever you want to, create or construct a foundation, you'll have to dig out the earth first. And then when you do that excavation, you'll have to support the soil wall surrounding it, so that way you can, allow workers to, work in safe conditions. And usually, the deeper your excavation becomes, the more sort of rigid, or the, sort of the higher in scale or the larger in scale these support structures need to be. Okay, so here are just some examples of some smaller scale short excavations or support systems. So here we have a shallow trench. As you can see, it's very narrow, and they're usually narrow because they don't need to be, because they're only really used to install, for example, utilities or pipelines. So they're very they're shallow and they're very narrow, and they also have these bracings here to support the wall. Also here we have sheet pile walls, which I'm sure you're very familiar with. They're these bracings that are sort of put in place to retain the surrounding soil, so that the workers here, the construction workers, can work, in very safe conditions. And these are used for sort of larger or wider areas, as you can see. And then here we have some examples of some deeper excavations for larger scale structures. So as you can see, these excavation bracings here support the wall to, brace against the soil pressure that's acting against each of these walls here. And we'll talk more about the sort of soil pressure and how to account for it later on in the presentation. And then also here we have some tieback systems where you can sort of drive these sort of steel reinforcements into the soil walls and to tie them back here at the end. And we'll discuss how to model these as well in numerical analysis. So when you do the design of your short excavation, you not only have to design, or you not only have to account for the soil pressure, but you also have to sort of find out the forces acting, on your wall as well as your anchoring systems. So that's something that we'll discuss, is how to not only model it, but also how to extract those results in your final post-processing. Okay, so now let's go over the design process as far as conventional methods are concerned. So the first step is to select the type of lateral earth pressures that are expected to act on the wall. So there are three types of earth pressures that need to be accounted for. The first is active earth pressure, which is the soil behind the wall over here that's sort of pushing up against it, that's causing it or trying to get it to fail. Then there's the at-rest earth pressure, which is soil pressure acting on the wall from sort of a faraway distance. So there's active earth pressure from the soil directly behind the wall, but then there's also soil from a further distance that's also applying pressure on the wall as well. And then you have your passive earth pressure, so on the opposite side of the wall, sort of beneath the, where the wall has been installed, on the opposite side of the active pressure is the passive earth pressure, which is, resisting it. So things to keep in mind is that active or at-rest earth pressures are commonly used. So these are the two main types of earth pressures that are acting against your wall. You need to consider the water pressure at poor drainage sites. So in addition to soil pressure, if you have a site with poor drainage or where there's clay soils that have water that hasn't been drained out yet, then you'll also have hydrostatic pressure acting on your wall. And then you need to multiply by the factor of safety as directed by codes, depending on where you're working. I suppose the safety codes might vary differently, so there might be different factors of safety. So it's really important to understand, or to get have a knowledge or an understanding of sort of the codes that are being used in your area as they apply to short excavations in the design of these walls. So once you have the types of lateral earth pressures calculated, the next thing you need to do is to apply external stability checks to ensure the overall stability of the shoring system. So this is done just by getting the ratios, or your factors of safety. So for your passive resistance of shoring systems, the factor of safety of the sliding resisting horizontal forces divided by the driving horizontal forces needs to be about a 1.2 minimum. So the resisting horizontal forces are simply the forces that are acting, that are keeping your wall in place. And the driving horizontal forces are your active, your at-rest, and your hydrostatic pressure acting on the other side of your wall. These are the forces trying to cause it to fail. So essentially for every, let's say it's in terms of newtons. If you have, 1 newton of driving horizontal force, then by this ratio you need to have 1.2 newtons acting against it, minimum. Now, as far as moment, the factor of safety of overturning resisting moments divided by driving moments has to be a 1.5, so it's a little bit higher. So that's something we'll discuss in the next couple of slides, is just how the moment needs to be accounted for in addition to the sort of sliding pressure or sliding forces. Okay, so next you need to determine the bearing stability of the wall. So it's critical if the wall is based on soil and not rock. So once again, it's critical just because soil is, naturally it's less stable. So if you're working in a soil conditions, or if your foundation or excavation is taking place in soil, then you have to, sort of take it under these critical terms. Whereas with the rock, it's more stable, so you can be more conservative in your calculations. Okay, so bearing stress on both the heel and the toe should be checked. So here's the toe and here's the heel. So you need to check the bearing stress on both parts of the retaining wall. Bearing stresses are checked against permissible bearing stress with a minimum factor of safety as 3. Okay. If not possible, then settlement control is critical. So if you can't get that minimum factor of safety 3, then you have to sort of take it a step further and go into settlement control. Which is sort of another remediation, which isn't really sort of the main topic of this session. But for those of you who have worked extensively with deep excavations, I'm sure that settlement control is something that you have to deal with from time to time when the bearing stress or the minimum factor of safety couldn't be reached just through these means themselves. Okay, so now the next thing you need to do is to check against the global failure. So if you go to the bottom right here, as you can see, we have a couple of different sort of failure types. So a global failure is caused due to failure of soil below the retaining wall. So if you look at these two bottom pictures here, as you can see, these lines here, these curves, represent the arc failure surface. So as you know, in slope stability, in soil slopes anyway, tend to fail in these slope arc, in these sort of arc shapes. So there are certain instances, or there might be certain, project conditions in which your soil, or excuse me, your soil could fail beneath the actual retaining wall, thus causing this moment or this overturning to happen. So this is something you need to check against. You need to find the sort of critical condition that would cause this type of failure. And is common in regions with weak soil strata or on hillsides. So naturally, if you're working in a project site that has particularly weak soil or on a hillside, this type of scenario becomes more and more probable for obvious reasons, just because the soil isn't as stable. Okay, then it's necessary to use numerical analysis on such sites. So for areas with particularly weak soil, it's best to use numerical analysis just because conventional methods are a bit too conservative and it's not really safe or realistic to use them. Okay, and then the next step is to check the shoring system for structural stability. So once you have sort of analyzed all of your soil surroundings, the next step, or the final step actually in the design process, is to check the shoring system itself, to check the structural members that you're using, and to find the forces, not that are acting on them, but the sort of the reactions to the forces that are acting on them. So it's necessary to check the individual components. So for example, the section size, the reinforcements, and the length, etc. So this is something that you can do with a numerical modeling program, is you can model your structural elements, and then you can check your moment diagrams, your axial forces, your shear forces, etc. And then accurate forces and members are essential for optimal design. So naturally, as engineers, you want to design the safest and most economic sort of structure possible for your particular project. So it's through the design of the shoring system, or anyway, you want to make sure that you design a shoring system that's safe but also optimal. You don't want to over-design your shoring system because you don't want to spend more than you need to. So that's why this step in particular is very important, just so that you can make sure that your design is very economic. And you would do that through designing the type of retaining wall that would not only resist or to meet the minimum factors of safety required by the code that's in the area that you're working in, but that are also very economic for your project site. Okay, so let's go over a quick summary of what we learned in this section. So 1, deep excavations. This means the removal of soil for a foundation and underground structure. Different types of shoring systems are available. Some that we mentioned briefly were shallow trenches, excavation bracings, tiebacks, sheet piles, soil nails, soldier piles, and lagging. So really, the sort of type of shoring system that you use really depends on the sort of excavation that you're doing. So naturally, shallow excavations would warrant shallow trenches or excavation bracings, whereas deeper excavations would require bracing systems that are more that are sort of larger in scale, such as tiebacks and soil mills and soldier piles. Then different shoring systems are used based on different site requirements, so it sort of reiterates what I just said. The design process of the shoring system includes the following. So it includes a governing lateral pressure determination, usually active or at rest earth pressure. So active earth pressure is the soil acting directly behind the wall. At rest earth pressure is the earth pressure acting on the wall from a further distance. The external stability, or against sliding, the factor of safety is or the minimum factor of safety should be 1.2, and overturning, the minimum factor of safety is 1.5. So overturning, that's the moment or the rotational forces acting on your bracing or on your wall. The bearing stability check is critical for poor soil, so it's a minimum factor of safety of 3, and settlement control might be needed if you have trouble meeting that factor of safety. Global failure check at hillside, soft grounds, and unstable strata. These need numerical analysis. Once again, to use conventional methods or just simple hand calculations for these types of projects will lead you to have results that are too conservative, or in some cases might not even be safe to use. So numerical analysis, which we'll discuss in this next section, has sort of several or can account for certain variables that conventional design can't. and then the structural design of each component with accurate design forces. So your final step, after you've determined, your minimum factors of safety as well as your earth pressure and your earth conditions, is to design the structure itself. So what you need to do is you need to check the forces acting within your support systems, just to make sure that they're safe, that they meet those minimum factors, or that they don't go past a certain critical state. And also, in doing so, you can design you can design a support structure that's not only safe but very, very economical. And numerical analysis and numerical software is particularly good at handling this, just because you can model all of your structural components, and the results will be calculated for you. And we'll discuss this or I'll give you an overview of this when we give our demonstration. Okay, so now we're on to Chapter 3, which is the numerical analysis of short excavation. So during this chapter, we'll discuss specifically constitutive models, as well as how to create a numerical model for short excavation, as far as the walls as well as the bracing systems. Okay, so let's talk about the earth pressure in the design process. So the biggest difference between the conventional method and the numerical analysis method is the application of the earth pressure. So for the conventional method, your main area of interest are the input parameters. So you have to calculate the earth pressures, and you have to apply the earth pressure on the wall. So that's your main concern. So the thing is, with numerical analysis, let me hit this point first. So this is good for a shallow excavation. So if you have a smaller scale conventional project, for example, like a trench type foundation, or a very simple small scale sheet pile wall, what you can do is you can use a conventional method, and even though the results you get will be conservative, they won't really affect the project cost or the project quality. So you can use a conventional method just because it's very easy to use and very efficient. However, for deeper excavations, the conventional method isn't very practical. So as far as numerical analysis is concerned, your main focus will then be, instead of input parameters, it'll be on the output results. So for numerical analysis, you have to have a certain skill set that applies to modeling. So the engineer has to create mesh for the ground as well as the wall. So you have to be able to understand how to use a particular tool, particular program you're using, obviously, to create these components. So you need to understand how to create mesh sets for soils as well as structural components such as walls or bracings. Then you also need to have an understanding of the constitutive models for soil. So typically, when you're doing a numerical analysis, you'll already have certain soil parameters ready for you. So you don't really have to worry about those input parameters. You just have to worry about or you just have to input them, and then you have to focus on analyzing the results that the program gives you. So as far as constitutive models, in order to really be proficient at numerical modeling, it's good to have an understanding of the various constitutive models that are available to you. And what we'll do during this presentation is we'll go over 2 specific constitutive models that are commonly used in shallow excavations. And then next, you have the stress and strain that are calculated based on the constitutive model and the external load. So actually, when you're doing a numerical analysis, you don't actually have to calculate the earth pressures yourself. All you have to do is have an understanding or have the ability to create a model for the program to analyze. And then once you do that, the program will calculate all the earth pressures for you. So once again, instead of having an understanding of how to model earth pressures, or not model earth pressures, but calculate earth pressures, it's really just comes down to being able to model them accurately based on creating the geometry and then also selecting the correct constitutive models. Okay, and then after the analysis, the engineer can obtain stress, also known as earth pressure, for each direction. So once again, this is something that the program takes care of for you. And then this is a must-use for deep excavation. So, when you go to get to larger scale projects, for example, if you're doing like an excavation for a high-rise building, that's very complex. There's going to be multiple construction stages, and then also the support systems or the bracing systems will be much larger in scale, much more complex. So, as you can imagine, the conventional method would not be realistic for that, just because there's so many variables that the conventional method can't take into account, that numerical analysis, however, can take into account. So that's one of the really the important things about being an engineer in today's modern world, is you need to have an understanding of numerical analysis at a very basic level, even just because it's something that everybody needs in order to handle those larger scale projects or those higher end projects. So if you really want to stretch your abilities as an engineer, Really, numerical analysis is very key in order to allow you to work on those larger scale projects. That being said, it's important to have an understanding of conventional methods as well, just because they've been around for a very long time, and they're very useful for those smaller scale projects. Okay, so now let's go into common constitutive models that are used in geotechnical analysis. So I'm sure you all have a basic understanding, or at least acquainted with, these various material models. So for example, Drucker-Prager, Hoek-Brown, these are typically used for rock type analysis. Modified CAM clay, which is used for settlement. Strain softening is used for settlement as well. Jointed rock is used for rock fissures or broken rock layers. So you should be acquainted with these material models. But the reason I have these two constitutive models sort of in bold here, the Mohr Coulomb and the modified Mohr Coulomb, is just because these constitutive models especially are used very commonly, especially for short excavation type projects. And what they do is they're for elastoplastic with hardening and softening and ambient influences, and then the modified Mohr Coulomb is used for elastoplastic with cap hardening. So let's discuss these two constitutive models in further detail now. So in regards to the application of the Mohr Coulomb model, it's used for soil shear failure, and it's used for equivalent linear stiffness for compaction or unloading behavior. So below here, these three pictures are just a couple of graphs that represent studies that are done to use the Mohr Coulomb model. Mohr's circle, which is very commonly used, and then also axial strain versus deviatoric stress. So it's through using these constitutive models that it's through using these sort of relationships that these models use certain empirical equations to determine the behavior of soils. And now for nonlinear and compaction and shear failure, you can use the advanced constitutive models called the modified Mohr Coulomb model, also known as a hardening model. So that's the main thing to keep in mind from this slide, is that the Mohr Coulomb model is used for sort of simpler, more straightforward numerical analysis, whereas the modified Mohr Coulomb model is used for more advanced analysis. So Mohr Coulomb is generally sufficient to model these specific types, these specific project types. So stability analysis for slopes, embankments, and abutments. Also ultimate load analysis, bearing capacity problems, punching shear. And then soil structure bond failure for ground anchors, soil nails, or geotextiles. So as you can see, this covers a very sort of wide array of geotechnical programs, and it covers ones that are sort of day-to-day or that are most common. So that's why the Mohr Coulomb model is so important to use and to understand, just because it's it's the one that's used the most often. So excavation problems for basic behavior. So if you have a basic sort of deep excavation, then the Mohr Coulomb model typically will suffice. Now, as far as your advanced models are concerned, the modified CAM clay model is required for the following. Settlement analysis of foundations and embankments on soft soils. So if you have like a project that's located on clay saturated soil where you'd expect sort of long-term drainage or long-term consolidation, then these advanced models would be used, just because there are certain parameters that the Mohr Coulomb doesn't take into account that need to be taken into account to realistically predict settlement over a long period of time. And then undrained or over-consolidated silts and clays, and then consolidation of soft soils. So once again, usually it's a combination of the modified Mohr Coulomb model and the modified CAM clay model that are used to do your settlement or do your drainage type analyses. And then deep excavations for detailed behaviors. So if you have, for example, if deformations in particular or in settlements are of particular importance to you, then the the modified CAM clay model would be, the modified Mohr Coulomb model is typically your best option, just because there are certain variables that the program, that the constitutive models takes into account that allows you to better simulate this detailed behavior. So advantages compared to the Mohr Coulomb model. So this is the advantages of the modified Mohr Coulomb model, or the hardening model, as opposed to the Mohr Coulomb model. So some of the advantages include better nonlinear formulation of soil behavior in general, both for soft soils and harder types of soil. Distinction between primary loading and unloading and reloading, so it's more detailed in that respect. The stress history of pre-consolidation stress. So if you have pre-consolidated clay that needs to be accounted for, you would use the modified Mohr Coulomb model or the modified CAM clay model. different stiffness for different stress paths based on the standard tests, and then it's suitable for unloading situations with simultaneous deviatoric loading, so for excavation. So, with your excavations, for larger scale excavations anyway, you'll have a lot of loading and unloading, especially if you have construction stage analysis where equipment's being taken in and out, or temporary supports are being put in place. This is particularly useful for simulating that. However, there are some things to keep in mind when using the modified Mohr Coulomb model. First and foremost, that it's difficult to obtain all the parameters. So, as I mentioned before, when you're using the modified Mohr Coulomb model, there are other parameters that need to be taken into account. And in order to get these parameters, you'll have to run sort of extra lab tests, really have to do extra research. However, some of the complications that arise from needing these parameters is that that it's not always you can't always rely on them as much as you would like. So sometimes, in some cases, actually, it might actually be better to use the Mohr Coulomb model just because the parameters are more readily available, they're easier to obtain, and you can have greater confidence in them. Whereas with the modified Mohr Coulomb model, there may be instances where you can't maybe get the parameters with confidence. Then it would be best just to go to the Mohr Coulomb model. Just because when you do any sort of analyses with these constitutive models, you really want to have good confidence in the input parameters that you use. Otherwise, the results that you get might not be as reliable as you would like them to be. So that's just the basic comparison of the Mohr Coulomb and the modified Mohr Coulomb model. And when we go to our sort of sample project, I'll show you sort of the different input parameters that are needed for each. Okay, so now let's discuss material behavior in the excavation process. So as far as unloading due to excavation, vertical unloading at the excavation bottom, horizontal unloading behind the wall. This may be accompanied by shear plasticity. And then primary loading due to pre-stressing. And then the modified Mohr Coulomb model is preferred for nonlinear elastic unloading and reloading behavior. And then shear plasticity due to horizontal unloading. And the stiffness is better for a prediction of trough settlement. So this is just, once again, the three sort of material behavior types that you need to keep in mind. So unloading due to excavation. So once the soil is unloaded from the sort of the top layer, the bottom layers are going to have, if they're clay, they're going to be over consolidated. So once again, you need to understand that relationship. Primary loading due to pre-stressing. So when you have your equipment or when your structures are being put in place. So you'd use the modified Mohr Coulomb model for this type of behavior if you want to analyze this type of behavior in detail. So now let's go into the summary of material behavior. So Mohr Coulomb, one of its weaknesses is that it has very unrealistic deformation. So the reason it has that is because it uses a single value of E, or Young's modulus, and this fails to cater to complex materials at various zones. So it's very conservative in that respect. You have a single value of Young's modulus when in reality the Young's modulus of your various materials differ from area to area. And also it overestimates the bottom heave, and sometimes it overestimates the heave of the soil behind the wall. So for those of you who have done or used the Mohr Coulomb model for your excavation projects before, I'm sure you've noticed that oftentimes you have this, when you're analyzing your deformations anyway, that the program that you're using will show you this sort of large heave at the bottom or behind the wall. And typically it's good to just take those as negligible. It's really due to something called the stress relaxation coefficient, which I don't want to go into detail now, but just keep in mind that when you're using the Mohr Coulomb model, these unrealistic deformations are just one of the shortcomings of it. And then soils below excavation behaves with E sub R. Soils behind wall behave with E sub 50. Use of E sub 50 is too conservative. So this is just once again reiterating that the use of a single E or a single value for Young's modulus leads to very conservative results. So for the advanced material or the hardening model, you can get qualitative realistic deformations. So soil stiffness for isotropic loading, shearing, and unloading or reloading can be catered for automatically in the model, so that's a huge advantage. More realistic bottom heave and improved settlement trough behind the wall. So just keep in mind that when you're using the modified Mohr Coulomb model, or any sort of hardening model, your deformations are much more accurate, and you can have much more confidence in the results you're getting with that respect. So for the Mohr Coulomb model, if you have a project site where settlement and deformation isn't a particular interest or concern to you, then you can sort of take these unrealistic deformations that you get in your model as negligible. Most engineers that I know, when they do this type of analysis, they just ignore the deformations and then just focus on the strains acting on their, or it could be the strains of their support and their bracings. Whereas if you have a particular project for whatever reason, deformations are or an area of large concern for you, then it would be best to use an advanced constitutive model, because the results or the deformations that you get are much more realistic and much more practical. Okay, so now let's discuss how to create a supporting system in numerical analysis. So here we have, different sort of supporting systems, anchors, and tiebacks. So just to explain this picture here, here are your bracings, your sheet pile walls, and then these lines here, these 1D elements, are your anchors, and then these lines here are your bracings. So if you're modeling anchors or tiebacks, you want to model them as 1D elements, or as line elements, and they're designed for axial forces, so you want to use truss elements. Now there are two types of anchors or tiebacks. They're bonded and unbonded. The difference is that with bonded tiebacks, they ensure nodal connectivity throughout the truss length with a soil mesh. So that's just another way of saying that throughout the length of the tieback, nodal connectivity will be established with the soil layer. So it's sort of hard to visualize now, but when you have your soil layer sort of input here, there's going to be a series of nodes that will be touching the anchors. So it's just really important, if you have a bonded type element, to make sure that those nodes line up with the nodes of your soil. However, for unbonded tiebacks, the truss should be connected only at the start and end with a soil mesh. So for an unbonded tieback, the only nodes that would be present would be at the ends. So there'd be like a node here at the very tip and a node here at the other end of the tip. That's for unbonded tiebacks. And then, of course, pre-stressing force should be applied axially along the truss for pre-stressed tiebacks. So as far as pre-stressing forces, most programs have a special feature for that where you can model it. GTS-NX has one as well, where you just enter in your pre-stressing, you select your elements, and then it'll be applied to those elements. Okay, so for soil nails, these are modeled as truss members, and then nodal connectivity should be maintained with a soil strata mesh. So once again, if you're modeling a soil nail, just make sure that nodal connectivity is established throughout the entire length of the nail. So there'll be a series of nodes going along the length of the nail, and they'll be connected to the soil, just like a bonded tieback. Okay, another important thing to remember when you're creating your excavation bracings is, well, first they must resist axial forces, so they're modeled as truss members, and they must be modeled as a single member, otherwise singular errors due to out-of-plane bending or of immediate members will occur. So this picture here to the left represents the proper way to model your excavation bracing. So as you can see, it's a single sort of 1D truss element or member, and the nodes are connected just at each side here. The picture here to the right just shows the incorrect way to model your bracing. So as you can see, there are 3 nodes going along the length of it. Really, there should just be a node at the end and over here at the other end. There shouldn't be any nodes between those. The reason that this is incorrect is just like the bullet point says. If you model it this way, you'll get out of plane bending just because of the way the nodes are set up, and that's that'll lead to very inaccurate results. So it's actually much easier to model bracings correctly as opposed to incorrectly. It's actually easier just to draw your lines from one node to the other. It's actually modeling it incorrectly takes more effort. So that's just another thing to remember before you run your analysis. Just make sure that all of your bracings are modeled as such that there's no nodes in between the tips or the ends. Okay, so then let's go into how to create a supporting system in numerical analysis. So if you look to the right here, we have 2 examples of support systems. One's in 2D and one is in 3D. So as far as 2D analysis is concerned, soil is modeled with plane strain. So these are 2D plane strain elements here, and it's designed for the wall itself is designed for axial bending and shear effect, and it's modeled as a beam element. So if you look to the right here, this piece here is a 1D element. And the reason it's sort of wider is just because a certain structural property has been assigned to it. But then another thing you need to remember is to ensure nodal connectivity. So along the length of this structure, there'll be nodes, and you have to make sure that each of these nodes lines up with a mesh that it's pressing up against. So the nodes need to sort of link together with the soil in order to get your proper deformations and your proper strains, etc. Now, when you're doing a 3D analysis, the soil is modeled with solid elements, also known as 3D elements. So as you can see, all of the surrounding soil here, they're modeled with these 3D elements. And then the wall itself is designed for axial bending and shear effect, and this time it's modeled as a plate element, not as a beam element. So if you look over here, as you can see the mesh in this area, it's a different color than the mesh over here. So this is just to let us know that this mesh consists of a different material property than this mesh. So this mesh, it represents obviously our retaining wall, and it's being applied where it has these 2D property, and the material property has been applied to it. So later on, when I show you my the demonstration of the project, I'll get you a better view of what that 2D planar element looks like. So just keep in mind that when you go from a 2D to 3D analysis, all of your elements sort of get bumped up a class. So your 2D elements for your soils become 3D elements, and then your 1D elements for your walls then become 2D planar elements. Okay, and then just like with 2D analysis, you need to make sure that nodal connectivity has been established. So the nodes of the retaining wall need to line up perfectly with the soil surrounding it. Otherwise, your analysis won't run. Okay, so now we'll move into a comparison of conventional and numerical analysis. Just a quick recap. So with a conventional approach, the soil behavior is modeled with Terzaghi and Peck formulas or empirical equations. Whereas with numerical analysis, you use the Mohr Coulomb and the modified Mohr Coulomb models, which are constitutive models. For earth pressure, it's based on an empirical formula, whereas with a constitutive model, you enter your parameters, and then your earth pressure is calculated by the program you're using, so it's an output. Excavation sequences can be considered in conventional approaches, whereas they can be considered in numerical analysis. So once again, for larger scale, lengthier projects where you have detailed construction or excavation sequences, numerical analysis is your only realistic sort of option. Excessive excavation-induced movement, it can't be considered with a conventional approach. However, it can be considered and simulated very realistically with numerical analysis. That's another one of its strengths. Settlement of soil at relative support, it's not possible with conventional approaches, whereas with the numerical analysis approach, it can be monitored through interface elements along the support. So that's another thing I'll show you very briefly during the demonstration is just the interface elements. And the design for a conventional approach for larger scale projects anyway is very conservative and expensive. For smaller scale projects, it's still conservative, but it's once again it's still economic just because of the sort of the project conditions. Whereas with larger scale projects, numerical analysis is very optimal and it's very cost effective. Okay, so now let's have a brief summary here. The Mohr Coulomb model is most commonly used, constitutive model, for slope stability, bearing capacity, soil structure, bond failure, excavation problems with basic behavior. So once again, if you have any of these projects, the Mohr Coulomb model typically will be your best option. For nonlinear compaction behavior required for settlement analysis on soft soils and deep excavations for detailed behavior, the hardening model, also known as a modified Mohr Coulomb model, is recommended. Excavation causes soil heaving due to unloading, which can be captured accurately with a modified Mohr Coulomb model. It can't be accurately captured with the Mohr Coulomb model, actually. And then the modified Mohr Coulomb model can vary the Young's modulus for soil as per a change in stresses, while the Mohr Coulomb model uses a single value. So that's another one of the Mohr Coulomb model's sort of shortcomings, is that it only uses a single value, which leads to conservative or unrealistic results, especially for deformations and settlements. The modified Mohr Coulomb model requires parameters from different field tests, thus it is only used on critical projects. So that's a shortcoming of the modified Mohr Coulomb model, is that you need to get these additional parameters. For bonded tiebacks and soil nails and truss members are connected with soil mesh at all points. For unbonded tiebacks, nodal connectivity is only at the start and end points. Walls in 2D analysis are modeled as beams, while in 3D analysis are modeled as plates. So once again, if you go to 2D or 3D, the element types that you use go up a class. Nodal connectivity with soil mesh must be ensured in both cases. That's very important. The conventional method is not suitable for deep excavations as it doesn't consider soil structure interaction, excessive excavation-induced movements, and relative settlement. And the numerical analysis considers the above and gives accurate design forces for optimal structural strength of shoring members. So once again, that's one of the key things to remember from this presentation is the sort of strengths and weaknesses, or the strengths of numerical analysis over certain project types, particularly larger scale projects. Okay, so now what I'll do is I'll give an introduction to GTSNX, which is our 3D finite element analysis software program. So one of the key strengths of GTSNX is that it's an all-inclusive software package. So it handles everything from static analysis, construction stage analysis, consolidation analysis, for settlement, seepage analysis, fully coupled analysis for stress seepage. So, for example, if you have a project where you want to analyze the effects of rapid drawdown on your project site, or if you want to analyze the effects of changing water levels, it's particularly useful for that. And also, the program handles seismic analysis. So if you're doing, for example, like a moving load analysis for a train, or for example, if you want to model your seismic loads, you can use the program as well. It does both response spectrum and time history analysis. Then, of course, it does slope stability analysis both in 2D and 3D. And then with GTSNX, you also have the option of using either the strength reduction method or the limit equilibrium method analysis. So once again, if you have GTSNX, you can use the program for any of these project types. So instead of having several different specialized programs for several different analysis types, you can just have GTSNX and handle everything. So this makes training a lot easier, and it makes integrating this particular tool into your company a lot easier, just because the program or the interface itself is very easy to learn, very easy to use. And once you get a mastery of it, you can sort of open yourself up to doing all these other project types with ease as well. Okay, so here's just the framework for the program. You have a ribbon menu that gives all your commands, your work window for your modeling, work tree that records all of your data, and then an output or a message window that for all of your commands. So what I'll do is I'll just give I'll show a brief video of the program in action that sort of goes over just the main modeling advantages that it has for you. So once again, you can change the background, you can select from a number of different languages. And as you can see, that ribbon menu is very sort of advanced in that it has these very large icons. It makes it very easy to recognize the commands that you want to use. So if you look here, as you can see, the engineer has sort of several tabs open at once. Each of these tabs represents a different project. So you can have multiple projects open at once in a single output, and you can go over them individually. And you can sort of go through your results. You can filter them, and I'll go over this in greater detail at the end of the presentation. It's just how to go through your results. But just keep in mind that the program is very flexible in that respect. You can have multiple projects open. You can go through multiple results simultaneously. Here, what the engineer is doing, he's going through the ribbon menu. He's going through a couple of the command options. So here, as you can see, all the commands, their instructions are included for each one. So for those of you, I guess, who are new to numerical modeling or who will be new to this program, it's very easy to just sort of start picking up how to use the program just by following those instructions that are given. So here we have the mesh generator feature you can use. You can control the sizing and the shapes of your meshing. The mesh generator is very quick, so as you can see, meshing is done fairly quickly. Then also, if you want to apply any sort of loads, you would just select your surfaces and apply them. So the interface is very user-friendly, very straightforward. Usually engineers that start using it within like a week or so, they'll have a mastery of the basic commands. Okay, so that's just the basic overview of the command system of the program. And then another great feature of the program is its advanced modeling features for complex geometry, specifically for grounds or for soil strata layers. So, for example, if you have maybe a 3D contour model that you want to import into the program and model, you can actually do that using the features that are available to you. So you can get a digital map in DXF file type and model it directly onto the program. Same thing with boring hole data. There's actually a bedding plane option that allows you to input the data for your various boring logs and create a very sort of detailed soil strata. So what I'll do is I'll show this quick video here, and it gives an overview of how to use those functions. Okay, so as you can see, you can just select the AutoCAD file directly from your computer, and then it'll import it directly into the program. So here's your 3D AutoCAD drawing, and here are your boring logs. So you can use this bedding plane option here to select the different boring logs. And then you would just select the boring logs, you give them a name for the bedding planes, and then when you define the bedding plane, you would just select the plane type or the depths. You just enter those depths directly for each of these boring logs. And then what the program will do is it'll record the depths for each of those boring logs, and then it'll extrapolate sort of the differences in depths to create, your various soil strata. Okay, so as you can see here, the different soil strata have been extrapolated just based on the boring log data that you entered. So it's something that can be done very quickly, very efficiently using this particular option, the bedding plane option. And now let's say we want to import that detailed contour surface. So using the terrain geometry maker, you can import your 3D DXF file here. Okay, as you can see, here's your side view and here's your overhead view. And now what you'll do with this is you'll use this information, or you'll use this data to create a sort of 2D planar surface that you'll then be able to import directly into GTS. So after you input your parameters, you would just select OK, and then here you have that very contoured planar surface, which is based on the drawing that you imported. So you would just save it in your computer, you would exit out of here, and then now you can just import it directly. So go to Terrain Geometry Maker, click Import, and here's the file that was just created. And then as you can see, you have your contour surface there. Okay, and then from this point, in order to create your 3D model, you would just create a 3D solid element for your soil block, and then you would use the clipping plane option, or not the clipping plane option, the divide option, to divide the soil block into the separate pieces. And then you would just cut off that top portion, obviously, or you'd delete it. And that would be how you would use, that modeling function. So as you can see, you can create a very detailed, very accurately modeled sort of model or soil strata within, with a very sort of easy and efficient step. So here we have, what we'll do now is we'll go over the results. So another great advantage of the program is that it has an advanced result extraction features. So what I'll do is let's play this video here. So here now we're in the result options, and as you can see, you can just sort of filter through the results very quickly with these options here. You have your various construction stages, and if you open up the drop-down menus, you can get your axial stresses for your beams, for your trusses, etc. Get your different contours. You can probe your results if there's a specific sort of value you want to see, maximum, minimum. You can click on these options here and it'll tag them directly on the project, on the work model for you. Okay, so translation, so it's displacement, etc. So here, as you can see, several tabs are open at once, so you can filter through various models very quickly. Then here's a tunneling type project. Let's say, for example, you want to see what the contour is like halfway through, or you're going to take a cut. You can just use this clipping plane option, which I'll go over again during the lab demonstration. But you can use that to get something very sort of distinct, or you can use it to get a very distinct cut along a certain plane or axis. Now, as you can see, it's time-based, so you can see how it changes with the different construction stages. You can show certain points. Okay, as you can see, so it's very easy to sort of filter through your results and to manipulate the display results in such a way that you'll see exactly what you need to see. Okay, so here's like a sample seepage project. So here we have like the total head. So as you can see, what you can do is you can filter the model to show a specific range of values, and the contour will fill in accordingly. Then also, if you want to see specific seepage results, so say you want to get your flow paths, what you can do is you can select a certain number of nodes along the length of your dam or your embankment, and the program will display your flow paths for you, as you can see. So it goes from left to right, so here's where your water is, obviously. And then, the contour bands show the sort of the speed or the rate of flow. So naturally, the red ones are the ones that are fastest. Okay, excellent. So now what I'll do before we wrap up is I'll give a quick live demonstration of the 3D retaining wall. So I actually have a completed project here, as you can see. So here is, my sample. Here's where my excavation is going to occur. And let me go over here. As you can see to the left, here's your work window where all of everything that you created has been recorded. So let's say, for example, I want to see what my excavation wall looks like, or my retaining wall looks like, along with the anchors. What you can do is you can turn off the layers or the sets that you don't want to see. So let's hide the conventional buried, or the colluvium, the weathered soil, and the buried layer. So here, and let's zoom in. As you can see, here's my retaining wall, and then inside here is my excavation. So I actually have these sort of excavation sort of slices separated. So I can turn these off, and as you can see, this is how my excavation will occur sequentially. So 3, 4, and 5. And then my final excavation sequence here. So as you can see, these are my anchors, and these are my bracings. These are modeled as 1D elements. So I believe these are unbonded, so there's no nodes. The only nodes will be at the end or at the tips. As you can see, there's little eye icons all over the retaining wall. So that's just to show my soil structure, or my interface properties. So if I scroll down here, if I look to the left, you see, oh, here it is, plane interface. So as you can see, I have a set of interface elements defined for my retaining wall just to simulate soil structure interaction. That's something that can be done very simply with the wizard, or the interface property wizard that's included in GTS. So now let's go take a look at our constitutive models. So as you can see, all my materials have been defined. But if I go to, for example, weathered soil, let's take a look at that. As you can see, I have my modified Mohr Coulomb model, and these are the parameters that need to be taken into account. So when you're using your Mohr Coulomb model, these would just be the main parameters. But with the modified Mohr Coulomb model, you have these nonlinear parameters. For example, you have your distant Young's modulus, that you need to sort of input, reference pressures, etc. So also, if you're using any structural materials, you go here. As you can see, I have structure turned on. This is elastic, so I believe this is for I think the steel for my anchors. So you just input this menu, and as you can see, it just has general properties. So since the behavior is linear, you don't have to worry about nonlinear parameters for that. And then, of course, you have your interface materials, which are defined with a wizard. That's very simply K sub n, K sub t. Once again, the program that can actually define that for you, if you enter in just a couple of other values, all this will be calculated for you through a wizard. And then also for your structural properties, let's take a look at, for example, my anchor. So as you can see, for my anchor, for these 1D elements, I have a specific section property assigned to it, which is the solid round shape. But you can choose any one of these shapes that you need for various structural properties and just enter in the parameters. And then once you assign it to a 1D element, the 1D element, or the program anyway, will recognize that the 1D element has that particular type, or section type assigned to it. Okay. So, and then also before I continue, I just want to show you that as far as the constitutive models are available to you, all of the models that I showed you in the PowerPoint are available to you in GTS-NX. So there's no limitation once again to any sort of constitutive models that you need to use. All the ones that are most popularly used or most widely used in geotechnical engineering have been included here for your convenience. Okay, so let's turn on this mesh. And another thing I want to show you is the construction stage analysis sequence. So something that we discussed in the presentation is just how with numerical modeling programs, or one of the strengths anyway of numerical modeling programs, is the ability to model staged excavation or long construction stage sequences. So in order to create that in GTS, it's very simple. Just go to stage set, and as you can see, I have my construction stage defined already. But let's take a look at it. So as you can see, in order to define your construction stages, you would just use these three input menus. So the input menu all the way to the left has all of the sort of mesh sets that you've created already, as far as your, as well as your boundary conditions and your static loads. And then this input menu here shows your activated data. So for example, we're in stage 1, foundation, pre-construction conditions. So this is everything that we want present in this construction stage. So right now, there's no retaining wall, there's no other loading, etc. It's just all of our soil layers. And you would just assign that by using the drag and drop option to move your selected data from the set data to the activated data. So now let's go into stage 2, install the wall. So as you can see, now I have my sheet pile wall, my interface elements created as well. And now if I go to stage 3, as you can see, now the excavation is taking place, and now this is sort of starting to be dug out. I've taken out the stage 1 excavation and I've installed struts and wailings, and I have different stages for each. So it's sort of sequentially that these struts and these wallings are being included. So as you can see, the excavation gets deeper with each stage. And each stage, one of these gets deactivated, so this is stage 2 getting taken out. Then I have, I'm installing my support system sort of sequentially here, and then finally I have my final excavation. Okay, so that's how you would do your construction stage analysis. It's very simple and straightforward in that respect. So now let's take a look at what our results look like. So after you run the analysis, let's go to post-processing here. After you run the analysis, if you have a construction stage analysis, you'll have several different cases to search through. So let's go to stage 1, displacement, total translation. So as you can see, it's all in blue because it's 0, nothing's really happening as far as displacement. But now let's go to stage 3 here, where I have my first excavation occurring. Let's check out our total translation. So as you can see, that area in red represents, where the settlement is starting to occur. And that's actually, if you go to the result options here, you can change sort of how your setting is showing. So right there, I had an exaggerated sort of deformation just to get a better idea. So there's a certain amount of heave taking place. But if I go to underformed, I can get something more realistic. So as you can see, I have my different sort of depths of settlement occurring. Or deformation occurring. And let's say, for example, I want to take a cut to see how the sort of settlement is occurring below that level there, below that layer. What I can do is I can use this clipping plane option, and I can move it along here, and I can, so let's say I want to see what the displacement is at these 3 different planes here. I can add them, and I can turn this on. And I can sort of filter this, and I have these 3 different planes. And then also I can use my probe result option to get different sort of values along these planes. I can get my maximum and my minimum value as well. And it'll all be saved in a spreadsheet for me. Another thing I can do, I can turn this off, on and off. And then also, if I have a certain range of values, let's say there's a certain critical sort of value that you want to measure, that you want to see the contour for, what you can do is you can turn this on, and then you can use this ISO value, and it'll isolate, or it'll just select a certain range. Also, if you go to here under surface style, it'll show you sort of a range of values, or certain values, and it'll show the contour for that particular value. And then, just like the clipping plane option, you can show sort of multiple contours simultaneously. Okay, so that's another, great option of the programs. It allows you to sort of filter your results like so. Now going back to our construction stage analysis, so as you can imagine, as I go deeper into let's go into the final excavation now, and let's turn this on. Let's see our displacements. So as you can see, now we have our total displacements. And also another great thing you can do is you can turn on your clipping plane again, and you can see how the results change for each of them. Okay. Now let's say, for example, we want to see the results for our retaining wall as well as our sort of our anchors. So what we need to do is we need to turn off all of the mesh sets except for, once again, our wailing, our struts, and our anchors here, and then our sheet piles as well. So then go to your results, and now in your results option, go to, for example, shell element forces, and then you can get your membrane forces here. Let's zoom in, and then you can sort of go through, your various your forces in various sort of different coordinate systems here, and then beam element forces. If you want to see with the beam element forces for your support or your bracings, you can check them here, as well as your moment in the Y, or your moment in the Y and the Z direction, so you can view everything. And then if you want to check your anchors, go to the truss element forces, and then you can get the axial force acting on your anchors, as well as the torque. So that would be how you would filter through your results for that. So once again, that's something that's really great about numerical modeling programs, is you can get your settlements, you can get your axial or your forces acting on your structure, and you can do so for a number of stages. So once again, if you want to go back to the other stage here, so let's say we want to see what it's like in stage 4, you can filter it here, and then you can get your truss element forces. As you can see, they change a little bit, and same with beam element stresses, or truss element stresses here, or excuse me, beam element forces. And then you can see how they change from stage to stage, and you can see sort of the progression that's made as the excavation and the construction sequence takes place. Okay, so that one last thing I want to share with you all before I wrap up for today is just the report generation function. So something that's great about GTS-NX is that it has a function specifically for report generation. So let's say you run your analysis, you like your results. From that point on, you just have to organize everything into a report that you can submit to a client or show to your colleagues. And that's something that can take a very long time just because the results in finite element analysis are so lengthy and so exhaustive. So in order to streamline the report generation process, the program comes equipped with a export to PDF function. So if you go here, what you can do is you can filter through all the results that you want to choose. So let's say, for example, I want to get my displacements for this and my for these stages, and let's say I want to get my beam element forces for this stage, etc. I can choose to have all these things included, and then I can import them directly into a PDF file. So in order to, as you can see, a warning shows up that it'll be slow with more than 20. So it takes a bit of it's a bit of a wait sometimes to get all the information loaded. So in the interest of time, what I'll do is I'll just show you a video that sort of gives an overview of the PDF function, or the PDF report generation function. So the video is located on midasgtsnx.com. So for those of you who want to learn even more about the program, feel free to just sign up and go onto this website here, and it'll have all the information for you. And if I go down here to this video, this will just show a brief sort of overview or demonstration of how the report generation function is used. So obviously this is for another project, but what will happen is your model will be imported directly into the generator. And just using these functions here, you can change the display settings to show exactly what you need for each page. And as you can see here, your thumbnail, so you can control or you can customize what's shown in each page. You can zoom in, you can show your mesh sets, your boundaries, conditions, or supports. You can change the angle very easily. If you want to have a cross-section, you can take a certain clipping plane. As you can see, you can cut it along any sort of axis to give a better view. Okay, so you can filter through your thumbnails, and then you can show your contour diagrams as well, and a legend will be included so that everyone who reads the report can have an understanding of what each of those contour bands represent as far as the numerical values, minimum and maximum values. You can probe it directly, so as you can see, the program automatically sort of selects or isolates your minimum or your maximum values. You can display those very easily. So it's very easy to customize these reports to meet like a certain vision that you have or a certain vision that you want to show. Cross-section properties. So once again, there are a lot of other sort of commands available, but these are just sort of the major ones. So here you can show your different cross-sections. And then also, if you want to show the dimensions, you can use this option, and it'll show the measurements or the dimensions of your project, and you can display them as you'd like. Okay, and then also if you have any sort of comment that you want to include, you can use that option there, and you can put like certain notes on each page or on parts of your project. So it's very, like I said, it's very easy to customize each page and to make each one specific to a certain vision that you have for your final report. Okay, so that about wraps it up for today's online session. I hope you all found it useful. Thanks again for taking the time to attend. If you have any questions, feel free to just send us an email, midasoft@midasuser.com. Once again, and I definitely encourage you to look into the program. It's something that's been very useful for a lot of our clients, and we hope that even more engineers will be able to take advantage of its advanced capabilities. For a free trial version of the program, just go to midasgtsnx.com and then click on this option here, download a free trial version. You'll be able to download the installation files. You'll have it free for 30 days. And then, one of our representatives will be in touch with you to help you get started with the evaluation, and we'll help you, maybe model any of your own or past or current projects on it. So once again, thank you for your time, everyone. I hope you have found this useful. I hope you found this informative, and we hope to see you again sometime soon. And have a good day.